Okay, sound, another form of energy. I'm just making that now, so one can do it a bit more severely, I suppose. So we create this air column that we vibrate, and vibrations become waves through the atmosphere. So I'm making sound as I speak. Obviously, when two things strike each other, we often see light energy. You can sort of scrape things off and get a bit of friction. There's a bit of light comes off. Sometimes you feel the heat that's come off, but also we hear that energy. I can feel my hands warming up, particularly because it's so cold in here. So that friction causes vibrations in the air particles around it. Now, some of those vibrations are in the surfaces. That's why we feel that warmth. But others become these sound vibrations. And they get collected by our ears. And we'll talk ears a bit later. So we talk about this thing called the electromagnetic spectrum. And as you can see, visible light sits about here-ish. And I often talk about ultraviolet light, so light further to the blue side, so getting these are faster waves, and infrared, slower waves to the high side there of visible light. Microwaves and radio waves on this high side, so slower waves. Things like gamma rays and X-rays, things that can cause more problems, cancers and things, tend to be on this faster wave. So these waves are really fast. They're packed together. But a guy called Maxwell suggested that these waves existed, and he thought they were made of magnetic and electrical components, which has been proven to be correct. And so light and sound are both part of this. So sounds, these slower waves, light's in this middle section. And Heinrich Hertz discovered radio waves in 1887. Of course, soon after, we've got people making devices to hear those and collect them and create them and send messages around the place. So I've sort of taken on a bit of a technological view of sound here, but if we think about radios, which we all hear regularly, an AM radio uses amplitude modulation, so AM, amplitude modulation, and it transmits sound at between 540 and 1600 kilohertz, after Heinrich Hertz. Now, these sound waves go for long distances, but the quality tends to be a bit low. FM radio, of course, people love FM radio because its quality is much higher. But if you want to drive out of Melbourne, the FM stations start to disappear pretty fast. So you can see they're between sort of 88 and 108 megahertz. And in recent decades, probably it's been a time I've been at Woodleigh, the last 20 years, digital radio has started to produce high quality, cleaner sound. But now the cost is that they're really short distances. So using digital radios is good in the city. Once you start getting out to the suburbs and beyond, it becomes a bit tricky because those radio waves are really short. So we have things called ground waves. I'm in the wrong place here. I'll give myself over there for a minute. Here's a ground with a radio transmitter, radio tower. The atmosphere is trapping that ground wave that's staying around Earth's surface. We pick up the sound at our homes. So it'll be our TV set, maybe pick up the transmission, or our AM radio. So they transmit on the ground, follow the natural curve of our Earth. Mobile phones, of course, use ground waves, but they need these regular repeater stations because obviously mountain ranges, cities full of tall buildings will block these radio waves, these ground waves. We talk, didn't want to change slide. We talk about sky waves as well. So sky waves use much more space. A space wave itself, you can see there, is not being refracted at all. So the sky waves tend to get refracted by the atmosphere, by the ionosphere. Space waves can go right out. So sky waves have a low wavelength, and they tend to get reflected back in by ionosphere. So you can send things a reasonable distance by using those. And as you can see here, where's my pointer? This aircraft is flying. It's able to use both the ground wave and a sky wave to stay in contact. Remember, that ground wave is going to slowly fall out. And of course, space waves. We can put our satellites up here and bounce things much further around the place. So again, we're allowing that wave of energy of the sound to be transported right up here into the ionosphere, collected by the satellite and then bounce back to a transmitter or a receiver somewhere over here. You get around that problem of ground waves that can't go around the bend of the Earth. So there's wave bands. And of course, we can't really go past sound without talking about your ear. So this thing here, the pinna, if you make your pinna bigger, even my own voice now becomes more clear. The pinna collects sound waves, and it channels those sound waves down the ear canal. And at the end of the ear canal is this membrane we call the eardrum. And it's like a drum skin. So that sound wave bounces against that and gets that vibrating. That vibrates this sort of thing here, the hammer, which vibrates the anvil, which vibrates the stirrup, and that vibrates in here into this cochlea. And the cochlea, like a snail shell, is lined with really tiny little fine cells, each of them tuned to different wavelength. And they vibrate, and that then gets sent through this nerve into the brain for the brain to interpret what that wavelength is all about. I've just done all that, haven't I? Look at that. I was going to throw that one with a picture. That's there for you to refer to later. So sound waves, all about energy vibrating, in this case atmosphere. Sound can travel through water, so it vibrates the water particles. So it's vibrating particles, and the wave then gets passed along. And those ground waves obviously can pass a long way following the contour of the planet, but they'll die out eventually. And we'll talk more about sound in class.